All right. Now let's look at this part of the interview where it's Dayspring again. Let's have you listen.
Cannot have atherosclerosis without a sterol, a lipid being in your arterial wall. And I know that arterial wall didn't oversynthesize sterols, creating a sterol buildup. Somebody had to deliver those sterols there, and that, of course, turns out to be a lipoprotein.
All right. So he's saying that atherosclerosis, those sterols that are in the wall of the artery are the reason for atherosclerosis. And the wall itself didn't oversynthesize sterols to create a backup or a buildup. Somebody had to deliver those sterols there. And that, of course, turns out to be a lipoprotein. So this is from New England Journal of Medicine, 2003, Intraplaque Hemorrhage and Progression of Coronary Atheroma. And they say, by contributing to the deposition of free cholesterol, macrophage infiltration, and enlargement of the necrotic core, the accumulation of erythrocyte membranes, RBC membranes, within an atherosclerotic plaque may represent a potent atherogenic stimulus. This is Frontiers of Physiology 2014, red blood cell hemoglobin and heme in the progression of atherosclerosis. They talk about plaque neovascularization, where we have inappropriate angiogenesis, formation of new blood vessels. These new vessels or neovessels are leaky and prone to rupture. The extravasation of red blood cells within the plaques then could happen after this rupture. And the cholesterol content of RBC membranes contributes to lipid deposition and lipid core expansion upon intraplaque hemorrhage. This is another one, International Journal of Molecular Sciences, and red blood cells and hemoglobin in human atherosclerosis and related arterial diseases, pretty much saying the same thing about how RBCs are contributing both to inflammation and the cholesterol content in the wall. All right. So now let's go back to what he said again. I think let's just take another listen.
Atherosclerosis without a sterol, a lipid being in your arterial wall. And I know that arterial wall didn't oversynthesize sterols, creating a sterol buildup. Somebody had to deliver those sterols there, and that, of course, turns out to be a lipoprotein.
All right. So again, he's saying the wall itself is not making these sterols. So this is a paper called Cholesterol Paradigm and Beyond in Atherosclerotic Cardiovascular Disease. What they note here is SREBP, remember that transcription factor, can be upregulated, turned on, right, in vascular wall subject to injury or something like stent implantation. So this transcription factor can be activated by pro-inflammatory and mitogenic factors in the vascular cells, in the walls of the blood vessel, leading to hyperactive mevalonate pathway, leading to hyperactive cholesterol synthesis, which promotes vascular cell mobilization, further pro-inflammatory and mitogenic factor release from vascular cells, and vascular inflammation. And they end by saying, targeting vascular hypercholesterolism could open a new avenue in fighting against atherosclerotic cardiovascular disease. So they're really saying that when you have injury to the vessel wall, inflammation, then you upregulate cholesterol synthesis within the wall of the blood vessel itself, which then promotes, the plaque formation and so forth. Now, we go on to another comment that he makes in part 2. Let's take a listen.
Jersey guy, one of my standard jokes on the lecture circuit was atherosclerosis is just a evidence of illegal dumping, where a lipoprotein, instead of bringing lipids to where we're supposed to be bringing it, was bringing sterols to the arterial wall. And you have to, it turns out in the long run, it's the number of ApoB particles that primarily is what forces it into the artery wall.
All right, so I thought worth looking at here. He talks about illegal dumpings. It's almost like they're sneaking in and illegally dumping their contents in there in the vessel wall. And then this idea of these particles um, forcing themselves into the artery wall. I thought maybe we should spend some time looking at this and getting a little clearer as to what is causing the LDL particles to move into the wall. So this is a paper, and basically we find that 85% of arterial lipoprotein delivery to the subendothelium is estimated to occur via transcytosis. So this is a regulated process, transcytosis, whereby these lipoproteins are taken in through endocytosis, right, into the cell. And it says here lesser amounts of lipoproteins are delivered via gap junctions or other processes. So, these cells are lined up against each other, and sometimes those gap junctions, the gaps between cells, become a little loose, and maybe things can force themselves or go through those gaps. But it turns out 85% of arterial lipoprotein delivery to the subendothelium is occurring through a regulated cell process called transcytosis. Now, in addition to LDL binding, ApoB100 contains at least 8 potential proteoglycan binding sites. The binding of LDL to proteoglycans is mediated by ionic interactions between the negatively charged sulfate and carboxyl groups of the GAGs, glycosaminoglycans, and the positively charged lysine and arginine residues in ApoB100. I did talk about this in episode 20 of the podcast when I was talking about the glycocalyx. So here, I did hear them talk about proteoglycans inside the vessel wall subendothelial layer of proteoglycans and how the ApoBs get trapped there, but they never referenced at all the glycocalyx. So we have actually a layer of proteoglycans outside the wall, lining the endothelial cells. This is well known, vital, but hardly ever gets discussed because these ApoBs are attracted through ionic forces. The proteoglycans and the GAGs, the glycosaminoglycans in the glycocalyx, the heparan sulfates, and so forth, they are highly negatively charged. Okay, and it turns out there are specific residues in ApoB that are positively charged. So anytime you have the ApoBs bypassing or going through the lumen of the blood vessel, they're going to be drawn to these negative charges, right? And that's, bringing them to this glycocalyx. They're not actually ramming or forcing themselves in there. Now we get to this study here, which focuses also more on the glycocalyx. And as I said, you can go to my episode on the glycocalyx for more details, but I think it's important to emphasize what's happening here when we're talking about ApoB at the vessel wall. So as I said, the glycocalyx lines these blood vessels. It is normally quite thick and lush and acts as a kind of permeability barrier because even though there are all these negative charges in them, they're embedded well within the layer, right? And there's some attraction of the ApoBs there, but most of the negative charges are within the thick layer of the glycocalyx. However, when we degrade or damage the glycocalyx and it thins out and we expose parts of it, now all those negative charges are exposed and the ApoBs can get drawn to those charges, right? And especially oxidized ApoB, because when we oxidize ApoB, we change the structure again, we expose more of these positive charges on the amino acids and it's much more positively charged than usual and gets drawn to the negative charges. We can also cause it to clump in different ways, right? So when the glycocalyx is damaged, then we lose this permeability barrier. And indeed, the ApoB now gets a lot closer to those endothelial cells, which can then transcytose the LDL in. Now, here in this study, they're looking at a mouse model of atherosclerosis, and they made these mice deficient in a glycosaminoglycan called perlecan. All right, so this perlecan is not existent in these mice, and as a result, we lose that permeability barrier. And as I said, now those ApoB particles can get a lot closer to the endothelial cells and get transcytosed into the cell. At the same time, because we don't have this perlecan, remember there are proteoglycans within the vessel wall itself. And normally that is what traps the ApoB there because of those ionic charges. But if we have Perlecan deficient mice, they don't have the glycocalyx. So, okay, we get more of the ApoBs entering into the vessel wall. But at the same time, because we don't have the perlecan within the vessel wall, we don't retain the LDL there, right? So that's really what this study is talking about. And I know there are complexities here, but I feel that we should really start now to look at these nuances and not just, kind of go with, oh, it's kind of forcing itself into the wall. And if you'll note, every time you look at a diagram showing this happening, often they'll just show the endothelial cells and then maybe ApoB, getting into the wall of the blood vessel, and completely missing from the discussion is the glycocalyx. And this is, really a problem here. And I think they missed an opportunity in this series to talk about the importance of the glycocalyx, especially we're going to talk about how ApoB gets into the wall, right? Because we have to now pay attention to the nuances, especially if we hope to elevate the discourse here, maybe to the level of a lipid fellowship. We want to start to understand what's happening and the different factors that are contributing to the ApoB getting into the vessel wall. So, I thought that I'd share that because I think it's really important. Again, details you can look up in the glycocalyx episode. Here we're talking about sphingomyelinase-induced aggregation of LDL. So sphingomyelinase is an enzyme that acts upon sphingolipids, right? Like sphingomyelin, where a lot of times in the lipid rafts. So these things connect. So this sphingomyelinase, when it occurs, it causes aggregation of LDL because it induces a massive global conformational change in ApoB, exposing hydrophobic motifs that adhere to each other, cause them to clump. All right. And so now we can have aggregation of this LDL. This is about, why we have retained apolipoproteins, and it says it's been hypothesized that specific cellular and molecular programs that cause immune cells to remain in place may have evolved as a defense against tuberculosis. So I did do an episode on this, tuberculosis and atherosclerosis, episode 52. I know little people thought this was a little crazy when I did it. Why is she talking about that? There's, I think, some method to my madness, I hope. But yeah, you can go and look at episode 52 if you're interested. But basically, retained and modified ApoB containing lipoproteins within the arterial wall elicit many of the same anti-migration signals as tuberculosis does. And this is another study from Nature Communications, and it looked at how the endothelial cells actually had a lot of the cholesterol crystal production that would be very toxic to the cell and promote atherogenesis. So my clarifications for this would be endothelial cells can modify cholesterol esters into toxic free cholesterol implicated in atherosclerotic cardiovascular disease. Injury to the vessel wall upregulates cholesterol synthesis inside the wall, and we call this vascular hypercholesterolism. Aside from lipoproteins, those red blood cells also contribute to plaque cholesterol. LDL is mostly transcytosed through the endothelial cell. It's not forced in. And ApoB has positive charges in certain amino acid residues, which are attracted to negatively charged GAGs in the glycocalyx. Again, you can look that up on episode 20.